Hello, this is Bruno. Today we'll talk about mesh analysis. In node analysis, which we learned last time, we put the voltage at each point of the circuit as the unknown and solved a set of simultaneous equations. It turns out there's another way to look at the same circuit and solve it. That is mesh analysis, which solves by taking the current flowing around the loops of the circuit as the unknown. Instead of going after the voltages, think of it as paying attention to the currents that go round and round. And today we will also cover how to choose between these two tools, node analysis and mesh analysis. Follow the steps and you'll be able to solve even complex circuits. So it's a very practical method. Please watch to the end. Before we get into the main topic, let me explain why we learned this method called mesh analysis. When we used Kirchhoff's laws directly, we put each current in the circuit's branches as an unknown one by one. That method is very powerful, but as the number of branches grows, the unknowns and the equations keep increasing too, and it gets hard to solve. So let's change our thinking. Instead of chasing each branch one by one, we pay attention to the current that goes round and round a loop of the circuit. When we make this imaginary current circling a loop the unknown, the number of unknowns drops sharply and it becomes possible to solve mechanically. Whereas node analysis last time paid attention to voltage, this time we pay attention to current. They are exactly the flip side of each other. That's the reason we learn mesh analysis. First, let me explain the star of mesh analysis, the idea of the loop current. For each ring, each loop that forms in the circuit, picture an imaginary current going round and round that ring. We call this imaginary current the loop current, or the mesh current. For example, if there are two loops, we place two loop currents, I1 and I2, one on each. These are the unknowns. Here, let's set one important rule. We take the direction of every loop current the same way across all loops, clockwise. Leaning them all up in the same direction means we won't get confused about signs later when we write the equations. Picture one circulating flow of water in each loop, and think of it as going after its strength. Next, how to find the loops that we place the loop currents on. A loop is within the schema, the smallest ring that contains no other ring inside it. Picture a window lattice. Each small pane made by the lattice, that is a loop. There are also bigger rings that go around the outside, but if one has smaller panes inside it, we don't count it as the smallest loop. And here's the important part. The number of equations to write equals the number of these loops. 2 loops means 2 loop currents and 2 equations. 3 loops means 3. The count drops sharply compared with counting branches one by one. That's the nice thing about mesh analysis. Next, let's write Kirchhoff's voltage law, KVL, for each loop. We learned KVL before. Going once around a loop, the total of the voltage rises and drops is 0. Going once around each loop clockwise, we write the voltage across each resistor using Ohm's law in the form resistance times the current through that resistor. Here is the single most important point of this method. Sometimes two loops share one resistor. Into that shared resistor, both loop currents flow in opposite directions to each other. So the current actually flowing through that resistor is the difference. My loop current minus the neighbor's loop current. For example, seen from the left loop, the shared resistor's current is I1 minus I2. In the equation, we write resistance times the quantity I1 minus I2. Once you grasp this, the shared resistor's current is the difference of the two loop currents. You're basically over the hump of mesh analysis. Let's sum up the flow so far in 4 steps. Step 1. Find the loops, the smallest rings, in the circuit. Step 2. Place a clockwise loop current on each loop. These are the unknowns. Step 3. Go once around each loop and write KVL. Write a resistor's voltage as resistance times current, and write the shared resistor's current as the difference of loop current. Step 4. Solve the resulting simultaneous equations to find the loop currents. Even when there are more loops, you do the same thing. Place a loop current for each loop, write that many equations, and solve them together. Now let's use these 4 steps on a real circuit. Now, a worked example. Let's solve a circuit with 2 loops. A 9-volt battery is connected to 3 resistors. The left resistor R1 is 1 ohm. The middle resistor R2, shared by the 2 loops, is 3 ohms. The right resistor R3 is 6 ohms. First place loop current I1 on the left loop and loop current I2 on the right loop, both clockwise. Let's write KVL for the left loop. The battery is 9 volts balances the voltage drops across the resistors. I1 flows through R1, and through the shared R2 flows the difference, I1 minus I2. As an equation, 9 equals 1 times I1 plus 3 times the quantity I1 minus I2. Tidying up, 9 equals 4I1 minus 3I2. Next, the right loop. There's no battery here, so the total is 0. I2 flows through R3, and through the shared R2 flows the difference seen from the right, I2 minus I1. As an equation, 0 equals 6 times I2 plus 3 times the quantity I2 minus I1. Tidying up, 0 equals minus 3I1 plus 9I2. Now we have a system of 2 unknowns and 2 equations. Now let's solve the 2 equations. Start with the easier one. The right loop's equation. 0 equals minus 3I1 plus 9I2. Tidying up, I1 equals 3I2. So the left loop current is 3 times the right loop current. Substitute this into the left loop's equation. 9 equals 4 times 3I2 minus 3I2. The right side is 12I2 minus 3I2, which is 9I2. So 9 equals 9I2. Therefore, I2 comes out to 1 ampere, and I1 is 3 times that, 3 amperes. Finally, let's look at the current actually flowing through each resistor. The left R1 is just I1 3 amperes. The right R3 is just I2 1 ampere. And through the shared R2 in the middle, taking the difference, 3 minus 1, 2 amperes flow. The answers came out cleanly, with no negatives. Now let's put last time's node analysis and this time's mesh analysis side by side and sort out how to choose. Node analysis takes the voltage at each point as the unknown and writes KCL, the current law, at each node. What it finds first is voltage. Mesh analysis takes the loop currents as the unknowns and writes KVL, the voltage law, on each loop. What it finds first is current. Pay attention to voltage or to current. They are exactly the flip side of each other. So which should you use? The answer is simple. Pick whichever has fewer unknowns. For a circuit with few nodes, node analysis has fewer equations. For a circuit with few loops, mesh analysis does, whichever makes it easier. In fact, the same circuit can be solved either way, and the answers of course agree. It's not that one is correct. You look at the circuit and pick the one with fewer steps. That's how the pros solve circuits. Before the check quiz, here's one field tip. The loop current simultaneous equations you just worked out by hand. The very same thing happens inside the circuit simulators the pros use. A circuit simulator, for example, software called SPICE, when you build a circuit on screen, automatically rebuilds that circuit into simultaneous equations and lets the computer solve them all at once. What it's doing is exactly the same logic as what you did by hand today. So once you know how to solve it by hand, it becomes clear what the simulator is doing inside. When you understand the insides of a convenient tool, you can also spot what's wrong when a result looks off. That's the strength of a pro. Now let's organize what we learned today with a check quiz. I have prepared 3 questions. Pause and give them a think. Question 1. The loop current is the equal current flowing through that resistor, true or false? Question 2. How do you write the actual current through a resistor shared by 2 loops? Option 1. The sum of the 2 loop currents. Option 2. The difference of the 2 loop currents. Option 3. Just one of the loop currents. Question 3. Which is correct about choosing between node and mesh analysis? Option 1. Pick whichever has fewer unknowns. Option 2. Mesh analysis is always more accurate. Option 3. Only one of them can solve it. Here are the answers. Question 1 is false. The loop current is just an imaginary current placed for the calculation. In a non-shared resistor, it happens to match the actual current, but in a shared resistor, the difference of the 2 loop currents is the actual current. Question 2 is option 2, the difference of the 2 loop currents. Both loop currents flow into the shared resistor in opposite directions, so the actual current is their net difference. This was the key point of mesh analysis. Question 3 is option 1. Pick whichever has fewer unknowns. The same circuit can be solved by either node or mesh analysis, and the answers agree. It's not that one is more accurate, choosing the one with fewer steps is the right answer. Now today's summary. Mesh analysis is a method that places a clockwise loop current on each loop of the circuit and makes it the unknown. Write a KVL for each loop. Write a resistor's voltage as resistance times current, and make the shared resistor's current the difference of the 2 loop currents. That was the biggest point. Solve the resulting simultaneous equations and you get the loop currents, and each branch's current too. And node analysis, which makes voltage the unknown, and mesh analysis, which makes current the unknown, are exactly the flip side of each other. Since the same circuit can be solved either way, pick whichever has fewer unknowns. That's the biggest takeaway today. Seen this way, last time's node analysis and this time's mesh analysis are a matched pair of tools for taking on complex circuits. That's all for today. Thanks for watching.